Welcome to Topic 1, Lesson 9. In this video, we're going to talk about gas laws. So you'll be able to compute gas problems involving pressure, volume, and temperature. We're going to understand the relationship between the gas law variables, as well as how to represent them graphically. And we're going to understand the difference between real and ideal gas behavior. So there are four physical properties of gases. We want to be able to represent them as variables. So pressure, we're going to use P. Volume, we use V. Temperature, we use T. Amount of moles, we're going to typically represent with N, as we've mentioned earlier. Here's a review video on the bottom if you need to recap some of the information taught in 10th grade. First, we're going to talk about Boyle's law. Boyle's law relates pressure and volume. All experiments were conducted at a constant temperature and constant number of moles. So we're just looking at the relationship between P and V, or pressure and volume. They are inversely related, which means that if the pressure increases, the volume will decrease. So let's look at the container on the right-hand side of your screen. On the left, we have gas particles in a container moving around. Remember, the particles are constantly moving in random motion. They're colliding with the walls of the container, and the pressure is the result of collisions with the walls of the container. In the picture on the right, we've now decreased the volume. So volume has gone down. We're pushing that piston in. And if now we look at what happens to the pressure, we'll look at all these gas particles. They're going to be colliding with the walls of the container more often. So the pressure has gone up by decreasing the volume. We can create this mathematical expression, P1V1 equals P2V2. We've seen this in 10th grade, so if you adjust the pressure, let's say the pressure goes up, the volume will go down. So since this relationship holds true, we could say that any pressure times any volume is equal to a constant. So this pressure times this value for volume will be equal to a constant, and we could set that equal to another pressure times another volume, because PV will always be equal to some value K. This is a graph depicting what Boyle's law looks like. We have pressure and volume. This is illustrating the inverse relationship, because as the volume is increasing, the pressure is going down, or as the pressure increases, the volume goes down. If we'd like to depict this as a direct relationship, we would say pressure is proportional to 1 over the volume. So sometimes that's a question that Ivy will ask you, is how do you take an inverse graph and make a direct graph? And here what we did was we just changed our axis to 1 over the volume. So Charles Lowe looked at the relationship between volume and how that changes with temperature. We have our four gas law variables, so we have pressure, volume, temperature, and moles. Charles Law is looking at temperature and volume, so that means that pressure and the number of moles were kept constant during all of his experiments. He figured out that temperature and volume are directly related, so here's a graph showing you a direct relationship. So as volume increases, temperature increases. As volume decreases, temperature decreases. What's important to remember is that the value for temperature must be measured in Kelvin, and all your gas law calculations we're going to be using Kelvin. So we have V1 over T1 equals V2 over T2. So since volume is always going to be proportional to temperature, we could say that volume divided by temperature is always equal to a constant. And that's how this piece of the combined gas law was derived. So we have volume over any temperature, we could set equal to a constant, and that's why we could set any volume over any temperature at any point in the data collection equal to each other. So if we look at some of the values in this experiment that were obtained, we look at the volume over temperature relationship, you see that it stays constant. So even though the volumes are changing and the temperatures are changing, so notice here that the temperatures were all converted into Kelvin, because we need, for calculation purposes, the temperature value to be in Kelvin. When we compare the volume and temperature value, V over T is always staying a constant value. So this holds true experimentally. Our last gas law is Gay-Lussac's law. He worked on the relationship between pressure and temperature. So if he's looking at P and T, that means volume and number of moles are being held constant. He found that pressure is directly related to temperature, so he developed P divided by T is going to be equal to a constant, or the part of the combined gas law, P1 over T1 equals P2 over T2. Again, it's showing you that as pressure goes up, temperature goes up. As pressure goes down, the temperature is going down. So this is a direct relationship. So P is proportional to T, or P over T is going to be equal to a constant, and that's how we get P1 over T1 equals P2 over T2. So the combined gas law now is just taking all three laws and putting them together. We have P1V1 over T1 equals P2V2 over T2. Remember, the temperature value must be in Kelvin. And pressure and volume values could be any units. It doesn't really matter as long as both sides are the same. So if I'm picking a pressure in kilopascals, I have to have the other pressure in kilopascals. If I have one volume in decimeter cubed, I need to make sure the other volume is in decimeter cubed, not centimeter cubed. They have to be matching in terms of the unit. Chart is very important here as far as a summary of what we talked about in this lesson. We have 3 laws we use, Boyle's, Charles, and Gay-Lussac, to build upon and make the combined gas law. We need to know what is constant in each law. So for Boyle's law, temperature is constant. Our equation is P1V1 equals P2V2. And we're talking about what's directly related or proportional. So pressure is proportional to 1 over the volume. For Charles' law, pressure is constant. Our equation is V1 over T1 equals V2 over T2. Temperature must be in Kelvin. Volume over temperature is equal to a constant, so we could say volume is proportional to temperature. Gay-Lussac, volume is constant. Our equation is P1 over T1 equals P2 over T2. Again, temperature must be constant, and the pressure is proportional to the temperature. So in summary, in this lesson, we need to be able to solve problems and analyze graphs that involve the relationship between temperature, pressure, and volume for a fixed mass of an ideal gas.